All right, good morning, everyone. Today we're going to be going over computer memory and linked list. Now, we've been talking about algorithms in the last couple of days, and we've been talking about efficiency, but we haven't really gone into computer memory or where those linked lists and other data structures come into play. Well, that's what today's going to be all about. Today, we're going to be covering memory during part one. It will be covering what is computer memory, why we should know about computer memory, what happens when I create a list, constructive versus destructive methods of creating a list and what's going on within the memory space, lists versus tuples, and then efficient code examples of what is efficient memory code. At this point, does anyone have any questions over the topics that we'll be covering today? All right, if there aren't any questions, then let's go ahead and get started. Well, the first topic today is what is computer memory? So computer memory refers to the hardware component responsible for temporarily or permanently storing data and instructions. This fundamental element is vital for computer functionality and data processing. Now, that's a word for word what we have in our curriculum. The way that I think about computer memory is just essentially how does the computer remember or how does the computer keep information in order to execute whatever functionality that I need it to execute. Now, there's two separate types of memory. There's primary memory, known as RAM, and there's secondary memory, known as storage. So primary memory is going to be something that lives within runtime. It's easily accessible, and it's also easy to throw away, right? The computer is going to execute, grab whatever information it needs to grab in order to execute its one functionality. And then once it's done executing that information, if the program or the whatever it is that we're utilizing has garbage collection, the computer will also grab it and throw it away for us. Now, if it's something that lives in storage, that's going to be a little bit harder to access. I'm going to have to maybe import a couple of things into my Python script to be able to access other files that live within my computer. It may be I may have to use specific permissions to even grab it. Maybe I won't even be able to use something like relative paths. There'll be a little bit of extra security around how to grab and manipulate those things. And most of the time, I actually won't even want to touch or manipulate all of that information unless I really, really needed to. So some examples of what a storage memory would be or secondary memory would be something like your hard drive or something like the solid state drive. So something really, really vital to your computer. Whereas primary memory is something that's just synchronous and dynamic. So when I run a Python script and I'm creating variables, any variable that I may create or anything that I may need the computer to remember for a specific amount of time, well, that would fall into my primary memory. And I think those are the two things that I really want to make sure that we get out of the types of memory. With that said, does anyone have any questions regarding the two separate types of memory? Should be pretty straightforward. All right. So moving on. Why is it important for us to know about computer memory? How does that change my ability to code? Well, there's a couple of things here. So there's something called resource optimization, right? And I have a little note there that says right data structure for the right cost. So if I'm choosing to create something, let's say, for example, we just recently did our assessment one. And in assessment one, we had to store a list of instances. Excuse me, everyone. I got a question here on the Slack channel. I will address that question during our next question break. So as I was saying, during assessment one, we had to create a list of instances, or we had to find a way to store different instances while our program was running and be able to grab and manipulate those instances. Now, there's a couple of different structures, data structures that we could utilize. right? We could have chose to utilize a tuple in Python, which could have chose to utilize something like a list, and we could have chose to utilize something like a dictionary. Rather, we did test-driven development, so it was dictated to everyone that you're going to utilize a dictionary. But now the question comes when it comes to memory efficiency is, well, how could I decide which one of those three should I use? So there's a tuple and a list, right? A list occupies a considerable amount of more memory than a tuple because a list must be able to be manipulated, right? It has different functions for inserting, for deleting. I could append into the list, and as I append into the list, the memory space grows. So because it has all of those built-in functionalities, a list already comes with the amount of memory space needed to be able to conduct all those functions. Now, a tuple is immutable, meaning that I cannot mutate a tuple. So if I knew that there was a certain number of users or a certain number of students or a certain number of videos in stock, then a tuple might have been might have been a better choice, right? It's still an iterable object. I can still search for something within a tuple, but it's fixed. I can't delete a value. I can't change a value. It's just a specific number of indexes that is expecting to a specific number of indexes where I can change the values within each index. I can't make the list grow. I can't make the list smaller, but I can't change the values within the index. And actually, we can't change the specific values within the index. It's just that since we're using classes, I can change the attribute within the class. We'll get more into that here shortly once we start talking about linked list. So that's resource optimization. The next thing is preventing memory leaks. So in Python and the languages that we've been using, like JavaScript, we don't necessarily run into this very much. But once you start using something along static languages, such as C, or I believe even C++ and C++, that doesn't do garbage collection for you. So garbage collection is the idea that after you're done using a variable or after you're done using a specific, you tell your computer that this needs to exist and you need to hold on to this information. When the function ends, it's not just going to dump all that information. It's not going to stop existing within your computer. You actually have to manually tell the program that once this function is done running, it needs to delete all of this information. So it's important to keep memory in mind so that you can prevent those things, right? You can prevent holding on to a bunch of junk that you don't need. You can prevent having a tuple that maybe utilizes 100 indexes, but out of those 100 indexes, nothing is being used, or maybe 3 of them are empty or they're none. You want to make sure that whatever memory you are using, you need it, or that it's there for a purpose. And then finally is performance improvement, right? How could I improve my code? How could I make my code more efficient? We talked about Big O, and Big O is more talking about the number of operations regarding the input and how efficient an algorithm can run. But today we're going to be talking about how we can make the actual code itself more efficient. Landon brought up a question a couple of times where he was asking, I get that binary search is cutting everything in half and that it's cutting it puts me into logarithmic time. But I'm writing more code and I could have more logic happening within each one of those if statements or each one of those while loops. So is that necessarily more efficient? So it's more efficient in big O concepts, but today we're going to be covering how we can make our actual code itself more efficient. So rather than writing a for loop to creating a list, we can write something like list comprehension so that the memory space is only created once for one list with all of the necessary information already placed into it. Whereas writing a for loop that would append into that list would actually just over and over and over recreate that list and extend the amount of space that list is taken over in the memory space. So although there are minute differences that we won't really be able to notice, they can change the efficiency of our code once we're working with large projects. So before we get into any actual coding examples, we're about to take a look at list, how they live, how they can change, where are they located in the memory. I want to go ahead and see if anyone has any questions regarding why it's important for us to understand our computer memory and the two types of computer memory. And I see that we have a question in the Slack channel from Adrian. He's asking if primary memory could be RAM. And yes, RAM does fall under primary memory. Any other questions regarding anything that we talked about so far? Okay, there are no questions. Oh, never mind. I see a question being typed into the chat here. Did you say languages like Python and JavaScript do garbage collection? Yes, that's correct. So Python and JavaScript and less dynamic, the more dynamic languages will do garbage collection for you. For example, C#, I know C# does garbage collection for you. But as they become more static, you'll see that some of them will lose the garbage collection functionality and expect you to dictate that for them. Does that answer your question, Terrence? Okay, awesome. And I see a question from Athena asking about how does list comprehension utilize less space. We're going to get into that here shortly once we actually start seeing some coding examples. Okay, so going off that question, we're going to go ahead and start seeing some coding examples. So we're going to talk about what happens when I create a list, right? Where does that list go? Well, let's take a look here. Let's say that I have a list of numbers and I make that equal to 1, 2, 3, 4, and 5, right? Well, what happens when I print the ID of list of nums? Let's see what happens when I execute this command. Well, when I execute that command, it's actually giving me some sort of number here. 4345025. I'm not going to read the entire serial number. But essentially what this is telling me is it's telling me the address of where this is being stored. So everything that we create whenever we're coding, it's actually being stored inside of our, I apologize, let me get that primary memory, inside of our primary memory. And when it's being stored, oh, I need to change that color. Okay, change that back to medium, change that to black. There you go. When it's being stored, it's not just being stored in a random way, it's actually being divided into our hexa memory. So if we take a look at something like a 32-bit, right? So here would be a 0, meaning at 0 bits, that's where that's located. Then we would have something like 32. Then again, we would have something like 64. And then finally something along the lines of 96 and 128. So all that we're printing out here by utilizing ID is we're printing out where inside of our computer memory, because this will obviously repeat over and over again into different rows. So we should see something along the lines of, let me try to draw this out a little better. There's going to be different rows within our computer memory where each one of them is taken in a 32-bit. And we can go ahead and store different information inside of each one of those, right? Now, I'm not going to go into how to interpret this information. You could learn a little bit about binary code as well if you would like to really understand how this is working or how it gets interpreted. But we can even print this as a hexadecimal. And when we print it as a hexadecimal, we get a more familiar interpretation of the memory space. Where else have we seen something like this before? In objects. Awesome. Yeah, thank you so much, Athena. So we've seen this before. Whenever we create an instance of a class and we try to print that instance without providing a string or representation method, right? This is showing us where this is being stored and is giving us the memory address of this specific variable, just like it did whenever we were printing our OOP instances. So that tells me where my list is being created, right? I know where my list is now living. Well, what happens when I start manipulating my list? And my list manipulation starts changing in locations. Well, let's see. Let's say the list of nums dot append, and we're just going to add the number 6 in there. Well, now I wonder, does my list still live in the same place? Or has anything changed? Well, I'm going to go ahead and run that. So we can see that at the hexadecimal level, nothing has changed. Well, now let's see if anything changed if I just do the ID. Perfect. So nothing has changed. My list still lives within the same spot. Even though I added a new value into it, my list still lives within the same spot. So earlier, I covered how a list, once it's created, it occupies a certain amount of memory space to be able to allow to be mutated, right? We have this append functionality so that we can send more numbers into it. We have the remove functionality so that we could remove numbers, but that's never going to change the memory location of that. It's not a construct. These are not constructive methods, right? These are methods that we are adding individual values into it without changing anything about my list. I can even change a value within my list. All right, I can say list of numbers at index 0 is equal to -1 instead of 1. And when I run this, even though my values change, nothing within my computer memory changes. Okay, that's good to know. Now, what if I was doing something along this? So list of nums, I'm just going to reference it as _2. And what this is going to do is it's going to be list of nums plus 6. Right? What happens when I do this? And rather than, well, first, let's make sure that this actually works. So let's print list of nums 2. I promise I can spell. And next, we're just going to go ahead and take a look at where list of nums 2 is located. So now when I run it, we can see the first space is being utilized the same way that we had before. Our list of nums still has the same memory address. Nothing changed. When I printed the hexadecimal of the location, it gave me the same exact result. Here I print list of 2, where I added the number to the end. But notice that when I added the number to the end, it now gave me a new memory address. All right. I can still name this list of nums. Maybe I just want one list of numbers, but what I'm trying to do is change the variable. But notice how they're different, right? They have different memory locations now. Why could that be? Can anyone take a wild guess? Go ahead, Brian.
Is it because it actually duplicated that list of nums into like a copy in somewhere else in memory.
Awesome. Yeah, that's a really good guess. What do you got, Tom?
Um, is this where pointers come into play? So like it's a we initialize I'm sorry, we basically made a new variable that has a new space in memory, but that variable at that space in memory is actually pointing to the other space in memory that the original data structure is occupying.
Awesome. Yeah, so that's a really good question as well. So let's go ahead and go over this. So I see Nathan saying that it's being reassigned. Well, here's what's actually happening, right? Let's say we have our little memory location here. And maybe I could draw this out a little bit faster here. Jeepers. Okay, let's go ahead and do that. So there you go. We have the specific list of numbers, right? And we're going to go ahead and store the first list of numbers. And we created a variable inside of one of these memory spaces. Well, here's where my variable lives. Now, this variable list of numbers, when it was created with the ability to append. It was created with the ability to remove. It was created with the ability to replace. I think there's also index as well in Python that we can all utilize. So all of those things were created within this one memory space. This memory space is tracking that I have this functionality. I can change all of that in this one list, right? Regardless of what values are also in there. I'm not just storing the values of the list, I'm also storing all of this functionality within that one memory space. So when I appended, when I did, let me go ahead and move this a little bit. When I did list of nums dot append 6, it didn't reassign this value. Nothing changed because this is a function that it has available to it, right? I can append something into my list. So it just said, hey, okay, well, if I'm appending something, I need you to stretch yourself out now and add a 6 in there. That's all it did. But when I said list of nums is equal to, I'm going to go ahead and shorthand this and say self plus a list that has a value of 6. This new list of nums, as soon as this equal sign comes into play, it knows it's no longer referencing the same memory space. This code is telling it that it's going into a different memory space. It's going to grab the original list and also add a list of the number 6 into it. So now we have a separate memory space holding different values that would look something like 1, 2, 3, 4, 6, and 6. All right. It takes the same list, it references it, takes its face value, adds the 6 into it so that we can get that 6, 6 at the end, but it's no longer assigned into the same memory space. It's actually falling somewhere new because of that equal sign. Right? It's being reassigned. It's grabbing the original value due to that pointer, just like Tom mentioned, but it's not actually being stored the same. This is no longer going to be referencing this list. Anything that I change to the list to the right-hand side is not going to be referencing this list on the left. It's only going to fall within this specific memory space. There's no link. It just grabbed the face value and created a new memory location. So using the equal sign is asking to putting out another bot. putting out another box and sticking whatever we want inside of it with all the things it is allowed or can do. Can you rephrase that question a little bit, Nika? I don't think I fully understand it.
So I'm just trying to make sure I'm understanding. So you were saying that with the first one, when we had the list of nums and we assigned the list to that variable, that's like having a box, and then you put out all the stuff that you can do with that piece of data in there. But then when you did list of nums equal to something else, it's like putting out another box with all the other things that it can do inside of it. I was just trying to ask for clarification to make sure I understand.
Yeah, exactly. So by doing assignment, it's saying that each piece of memory space is holding not only the value of what it is that you're trying to hold within this memory space, but any functionality that comes with that data structure. Does that make sense?
Yes, thank you.
Of course. And then I see Albert has a question saying, why wouldn't it override the original memory space? Yeah, that's a great question. Well, this is called contiguous memory, right? It's not something that we can just we can specifically tell it to overwrite in Python. We could probably go over that later on. That's not really something we're going to be covering here today. But essentially, as this is running in runtime, it's going from left to right and checking each individual memory space. Well, it says, hey, the left one is occupied. I can't utilize this list of nums. Sure, it's the same name for the variable, but it may not hold the same value because I'm using an equal sign. I'm using a reassignment. I'm telling it that this is going to hold a separate value. It's no longer going to be the list of nums that are originally created. But the program's not done running, so this memory space is still being occupied. So it says, well, since this memory space is occupied, I have to go to the one to my right-hand side and store this new value in it. Does that make sense, Albert?
Yes, thank you.
And then I see Athena asking, are both boxes still being utilized, or does the first box get deleted? So while in runtime, both boxes are being utilized, right? Even though from now on in my program, when I reference list of nums, I'm going to be referencing the second box. This one is already filled. And as long as my program is living, this box will remain filled. Does that answer your question, Athena?
Yes. Is this at the RAM level or have we not gotten into that?
Sorry, could you say that again?
Is this at the RAM level or have we not gotten into that?
This is at the RAM level, correct. Brian?
You know, in the red box is one of the reasons it's hanging on to the original list of nums, because to optimize, it's actually keeping that and using that reference in the new memory space and just saying, hey, with that new reference, I'm just lengthening it by one. Whatever that old reference is, I'm still using that, and I'm just appending a six to that so that actually there's no duplication happening in memory. I know it's kind of a weird question, but does that make sense?
It does. I understand your question. You're asking if there's anything relating these two, right? Are they referencing one another in order to make sure that there is efficiency? I'm trying to find a color that would be easily visible, but I don't think I could find one, right? That's along the lines of what you're asking, is rather than recreating its entire statement, is it just saying self is equal to this? And every time I reference that first memory space, is it running this operation under the hood all over again, right? That's your question, Brian?
Affirm, yeah.
Okay, perfect. So although that would be more efficient, that's not actually what's happening, right? What's actually happening is this is getting stored. And even though we're doing variable reassignment, this is already living within memory. And because we never deleted it, it's going to stay living within memory as long as my program is running. Once my program is done running, garbage collection will happen and all of this will get deleted. But this isn't referencing the original list. It's creating a copy of it here in self and then adding that six so that this is the new value stored here along with all of the functionality. Does that answer your question, Brian?
Yeah, it does. It makes me wonder if we can grab that hex value and print out the contents of that original hex value and see what it spits out. Does that make sense, to see if it actually does spit out the original list? I don't know if that will, Python will allow that.
Yeah, we'll have to experiment with it later on in the class. I think that might be a little bit too far from what we're covering today, but that is definitely a good one. We'll have to check it out afterwards. All right, Will?
Yeah, so the first list that was initialized, is that like a dynamic amount of memory that's like allocated to it, or is it like static?
No, so both of these are dynamic. That's why they're living within our RAM space, right? These are both going to be dynamic and they're going to be evolving depending on what we want to change into it. Does that make
Okay, gotcha. Yeah.
okay? Tom?
Sorry, just one final question. So when doing this, like when we're talking in terms of like efficiency and stuff, would this be like way more inefficient than simply appending, because now we're allocating more memory space to an entirely new instance when we could have just, like, let's say, appended that 6 into the first list?
Sorry, Tom. Could you say that one more time? I apologize. I was copying a question from the Slack chat into the, from the Zoom chat into the Slack channel.
No problem. I'm just asking, so in terms of, like, we're talking about efficiency yesterday and stuff, would this be way more inefficient than just appending the 6 the first time, because we're allocating a whole new space in memory for a new instance of a list, when, like, instead of maybe reassigning the list and creating a new list with that 6, we could have just appended it to the first one?
Yes, that's correct. So it would be more efficient to just keep the original list and append it, since we have that functionality and that memory space is already being utilized, rather than doing something like the example on line 3, where we're reassigning a new variable named list of numbers to a pre-existing value, which is 1, 2, 3, 4, 5, 6, and adding the list of 6. It would have been way better off just appending. Awesome.
Thank you.
Of course. The next question I have here is the second box dependent upon the first box, even after the reassignment is complete? It is not. So once the assignment is complete for the second box, this box could be deleted. It could be changed. So let's say I name this, I threw this back to 2, right? And let's say after this, I did list of nums dot append 6, right? And let's make sure that this is a little bit different so that we can see both differences. All right. So if they were dependent upon one another, then what I would expect to see here on the second box, sorry, let me minimize this again, is I would expect to see something along the lines of 1, 2, 3, 4, 5. I would expect to see the 6 and 7, right? But if the first list was, if this was still dependent upon the other, I would be inserting a 6 right there. All right, that would be the end state that we would see when we print this statement. But when I run my code, we can see that nothing changed. I still see 1, 2, 3, 4, 5, 6, 7, because even though this was appended, it never changed the value being occupied on list number 2. Regardless of whether I changed the name of the variable or not, what I am doing is a variable assignment. It's just I'm utilizing the same variable. Does that answer your question, Terrence? And I apologize, everyone, but please put your questions into the Slack channel. Okay, awesome. The next question I have here is from Roger. Roger says, how much memory space do you have to work with before you need to move whatever is in that space to another space with more free space? Okay, I see what you're asking. You're asking, well, what happens when that memory space gets full, right? If that memory space is full, or how would I know if that memory space is full and when to change that? If you utilize something like a list, we got to remember that the number, whenever we type in the number 1 or the number 2, it is a very minute amount of space that's actually being occupied. You shouldn't have to worry about managing the space relocation, or if you're gonna fill up an entire space, unless you're writing something in a static in a really static language. So when I say that, if I were to provide an example, in Python, we can do something as simple as, hey, this is a list, and I want you to remember this is a list, and I want you to hold it. Well, in something like C or C sharp, I think in C sharp, this is a thing as well. I can't just write a list. I have to tell C sharp, hey, I need a list that's going to have 10 spaces within it. And then C sharp will create that list with 10 spaces, holding the numbers 0 through 9. But then I could manipulate those spaces myself. Now, if I go anywhere over those 10 spaces, the program will tell me, hey, you don't have any more space here. You can't put anything into this list. You're out of space. You need to figure out a different way or create a new list that will have this list that will have this space into consideration. But this one is full. This is how it works in static languages. But in something like Python, we don't have to worry about that. Does that answer your question, Roger?
Yes, thank you.
Of course. Okay, the next question I have here is, what is the benefit to keep code in the same memory, less runtime? Yeah, that's an awesome question. So in our own local machine, we'll see that pretty much everything gets executed at a really fast pace, unless your computer is struggling. Those of you that were there for InstallFest, and I was leading InstallFest for WSL, I have a dinosaur of a Windows computer, and all of you saw that. Like it was struggling to get WSL installed and running. Right, I had to restart it a couple of times. Now, with that said, when we go to push our projects into deployment, what's happening on the web is that every single address that you go to, or every single URL that you go to visit, is attached to, I want to compare it to something like WSL, right? It's attached to another machine or another instance that's supposed to mimic a machine. Now, this machine is in charge of hosting whatever it is that you told it to host. It's going to render your own application, only your application. But if you want to keep things cost efficient, you want to utilize only the amount of memory space that you need in order for your application to run well for the user, right? So what does that mean for us? So for us, necessarily, it doesn't mean much because we're not going to be creating massive projects, right? But think about it if you're working for something like Facebook, or if you're working for Google, or a massive tech company that has a massive application that's utilized by hundreds of thousands of people. Well, at that point, it really does matter how much memory you're utilizing, right? It matters if you're using list comprehension versus utilizing a for loop to create a list. At that point, every it's kind of like when you go for a hike, ounces equals pounds, pounds equals pain, right? Well, think about that in computer memory now. Every single extra bit that you use makes your program less efficient, and it makes the computer have to think about what it's doing more and more every single time the operation is being executed. Does that answer your question? I think that was Jasmine that asked that.
Yes, yeah, that makes sense. I think it just will be a good approach. Just keep an idea on this, like what code that actually can make the runtime, less, something like that.
Awesome. Yeah, we're definitely
Thank
about.
you.
Yeah, we'll get into that here shortly. All right. There's a couple of other modifying methods that are here in our lecture, but we don't necessarily need to cover them. I think we all understand we can modify the original list, still keep that same memory space, but the moment we do something like reassignment, then we are occupying more memory. At that point, we're doing a constructive action. We are constructively creating a new list that will occupy more memory. So now the next thing that I want to talk about is list versus tuples, right? And this is going to give us a pretty good example over how we can make a small choice in Python. So now we already have this list of numbers. I'm just going to go ahead and comment out these print statements here. We have this list of numbers already made, and it has the numbers 1, 2, 3, 4, and 5. Well, now what if I make a tuple of numbers? And that tuple of numbers also holds 1, 2, 3, 4, and 5. Both of them are occupying 5 indexes. Both of them are occupying the same values, but I'm going to go ahead and import sys so that we can actually see the size of these two I don't want to call them attributes, variables. I apologize. All right. So now I'm just going to go ahead and say print sys dot get size of, and that's going to get me the size of the list of numbers. And now I'm just going to do the same thing for the tuple of numbers. Now, when I run this, since they're both the same amount of indexes and they're both the same amount of values, I would expect them to hold the same amount of space within my memory. But when I run this example, I can see that my list is using more memory than my tuple. Why is that?
And it was because of the mutability of the list, like all of that functionality to be able to change a list requires it takes up more space, whereas a tuple is immutable, so it doesn't take up as much space.
Right. The list is already built out to be able to be mutated, right? It has all of these functionalities made into it so that we can make our list bigger. We can insert at the beginning, we can insert at the end, we can append, we can remove, we can use pop. We have all of these different functions with the list that we can utilize to manipulate the different values within our list. While in a tuple, I don't really have much. A tuple, it's iterable, and I think there's like a joint function that I can do to like join all of those momentarily, but that value doesn't get returned under the same variable. That would have to get stored somewhere else if I wanted to keep it. So the reason why this is smaller is because my tuples functionality is pretty straightforward. It tells me this is the amount of spaces that you have. If you need to change it, you need to figure out a way to either create another tuple or use something different. And if you want to change anything, but this is set in stone. This is all I'm going to do. So it uses the very minimum amount of memory as possible. So that's just a quick example over how we could choose the correct data structure, right? If I'm doing a calendar, I know the only days are Monday, Tuesday, Wednesday, Thursday, and Friday, and then Saturday and Sunday, right? If I know that those are all of the days, well then that's all I need to worry about. I see a question here on the chat from Landon. And Landon is asking what is size of returning? And I see David said probably bytes. Well, let's take a look at here. Let me see if we can figure that out. Get size of. Oh, it's not going to show me. It's not showing me, and I apologize for not knowing off the top of my head. But I will get that answer to you here shortly, Landon. If not after the lecture, please reach out to me during the break. All right. So now the next thing that we're going to be covering is some memory considerations, right? And I'm just going to show us this quick example here. Let's say that I have a function named greeting. Now this function doesn't take any arguments, but it returns hello. Oh, hello. There you go. So now I'm going to create a variable named result, and I'm going to give it this list. And what I want this result to do is say for X in range 100, I want to result dot append the greeting function. All right, well, at the end of this result, if I go to print it, it should just hold hello 100 times. All right, so I go to print it. We can see that it holds hello 100 times. That's great. Well, now, if I go and I say, I'm just going to call it efficient result. And I say this efficient result is equal to a list of greeting for X in range 100. Now, if I run this, we can see that both of them, we have two lists. Oh, I didn't print the second result. Yeah, we can see that now I have two lists named result, right? And both of them print hello
So
100 times.
print the efficient result and not the result on the second one.
Thank you, appreciate it. Good catch. All right, so there's our second result. It holds our hello 100 times. And there's our first result 100 times. Well, now let's take a look at what's going on if I do sys.get size of. I just want to see the size of both of them. Well, now when I see the result of both of them have 920. All right. And let me go ahead and tap this in a little bit. So both of them utilize the same amount of size within computer memory. But even though they both utilize the same amount of size, let me move this up here. I'm going to go ahead and tell us that line 21 is more efficient in memory space than line 17. Can anyone take a guess as to why that is? Go ahead,
Is it
Brian.
because you're not,
Go ahead.
this is just a guess. I was just gonna ask, is it because you're not asking the computer to loop and to append in order to change the list?
Okay, I'm not asking the computer to loop and append, right? It's still falling within the result, but the method that I'm going about creating this variable or actually occupying this memory space is different. And I saw a hand up. Who Landon, go ahead.
Francisco, I was just gonna respond. I'm guessing because the for loop is like a different notation of big O, so maybe that's like ON. Then maybe your efficient result is executing another big O that's isn't as steep on the XY graph.
Okay, yeah, that's a good observation as well. And that definitely does apply. What do you got, Brian?
I think what Landon said is spot on. Also, it relates to how we started this, where the initial result size is unbounded. And so the computer just takes a guess, gives it like an initial size. And then every time we append it, it does what we did before with the 1, 2, 3, 4, 6 list. It actually will have to create more copies, larger and larger every time. It just keeps growing because it can't predict the initial size. And so, yeah, like Landon said, every time it has to recopy, that's like an n squared cost, and it's an additional memory cost. Whereas with the efficient result, it kind of can guess up front how much size this whole thing's going to take because of that range.
Awesome. Yeah, that's a good that's a good observation as well, Brian. Tom?
Also, like, so in the first result, like we declare the list variable. So it's creating like a dynamic space in memory, and same with efficient result. But you had in both you're iterating the same amount of times, but in the first example, you're using another method. So you're adding more runtime in because you're adding another method within the for loop, you're basically calling append and then greeting inside of the append, versus in the second one, you're calling greeting for each iteration of the loop, and you're not calling that other built-in method append. So you're saving one runtime method every time you're or when you call a efficient result.
All right, awesome. Well, now let's take a look at this, right? So whenever we're doing this result here, right, we're not necessarily creating a list every time, because we know that the list is already created and it has the ability to append. But let's go ahead and do a sanity check here. And let's print out the hex ID of result to make sure that we're looking at the same memory space. And let's also print out the size of result. All right, I'm going to go ahead and comment my second result here. Now I'm going to expect a bunch of numbers to happen. Let's take a look here. So we can see that it's always occupying the same memory space. Nothing changed, right? It knows that all it's supposed to do is fall within that same memory address, because that's where that variable is always going to be found. That's where it's being stored. All right, it's not reassigning itself anywhere. But look at the memory, how it changes every time. Right, keeps itself at 88, then it jumps to 120, eventually it jumps to 184, and it continues jumping up depending on the size of it until it turns into 920. Now, I'm not reassigning the memory space, but I am changing the value that that memory space has to grow. Right, so that memory space could be growing and growing every time I loop. Whereas in my second method, my computer doesn't have to wait until this entire operation, or it doesn't have to mutate the size of the memory space that I'm utilizing anymore. Instead, it already, before it occupies any space in memory, it runs this operation, determines the size, and then gives it a memory address. So when this when this efficient result is created, my computer already knows the size. It already knows it has to be this big in order to fit my list comprehension. I have greet for X in range 100. Right, so my computer already knows how much memory space it needs, whereas in the first example, it created an initial list, and then it continued existing within my program and slowly became bigger and bigger depending on how much size I actually needed for my list. And that's why line 23 is more efficient than this for loop up above in line 21. It's not about the end state sometimes. Sometimes it's about the process to get to that end state. That's why it's more efficient. Does anyone have any questions regarding this concept? Yeah, man, Terrence, like you wrote it on the chat. Thank you so much. Saul?
Yeah, so does that mean that the memory being taken up from the beginning is going to be 920? Like it's not going to grow like the other one?
So it could grow later on, right? I could still append into it and then grow it. But what we need to pay attention to is how much of the memory space that I occupy at first. So the first method of creating a for loop first occupies absolutely nothing. It only occupies this much space, right? Which we saw was, sorry, let me go ahead. I think it was like 80. Yeah, so we see that it occupies the space of 88, right? That's all it's holding. And then through each individual iteration, it began to grow. Whereas the second one never did that. The second one didn't allot any space into my function until it knew exactly how much space it needed. The space it needed was determined prior to creating the list, rather than giving it space first and then mutating that space to fit the amount of values that I needed. Does that answer your question? And I'm so sorry, but I lost your icon, so I don't know who that was.
It was me. Yeah, I did. Thank you.
Okay. All right. I don't see any other questions in the chat. So for part one, in conclusion, today we covered what is computer memory, why we should know computer memory, and the different things to keep in mind. We learned how to create a list and where that list lives. We learned constructive versus destructive methods of creating or manipulating a list. We compared lists versus tuples and how much memory space they're actually utilizing and why. And we did a quick comparison of efficient code when it comes to list comprehension versus a for loop. At this point, does anyone have any questions over any of the topics that were covered during the lecture? All right. If there are no questions, that's going to conclude the first part of our lecture. I'm going to go ahead and pause our recording. All right. Welcome back, everyone. We just finished going over memory and what's the importance behind knowing computer memory during the first portion of our class. And now during the second portion of our class, we're going to talk about linked list. So before we even start getting into the idea of linked list, I want to go ahead and cover what's the problem with list, right? Just list in general. What's going on when I happen to create a list? Well, when I create a list, I am not necessarily creating something that works independently on its own. I'm actually creating something that, again, has contiguous memory, right? And if we remember from earlier, contiguous memory means that it flows in one specific direction, right? Regardless of what I do here, this memory allocation will flow from left to right. Well, now let's think about it this way. Let's say I am writing an application where I want to store users inside of a specific list. Well, when I run my list, it's going to store user 1, user 2, user 3, etc. Well, now, what happens if there is a user that's no longer being used? I no longer need it, but it's already occupying something within my list. Well, when it goes to create the next number of the list, or let me see, something that might be better. When it goes to create the next member of the list, it's going to check that that spot is already full. And it's going to know, well, since this spot is full, there's really nothing I can do, right? So it goes and it occupies the next one. So there's my second user. Here's my third user. Well, now here's a user that I'm not going to use, right? But I still need them to exist for whatever reason. Well, now when I create my next user, rather than connecting it to one another, it's happening on the next location. And same thing, every time that gets used, gets created on the next location, right? And that link is happening continuously. I will have to remember this unless I manually tell my program how to handle for this one deletion. Well, it's not necessarily a problem in Python, right? Because in Python, we have some pretty flexible ability to change things. But what's all right. You have a mic on, and that was a pretty loud yawn, whoever that was. So
Was
yeah.
sorry, I'm hunting for the hot mic. Yeah, anyway.
Continuing forward, I apologize if I'm boring you. Moving on forward, we see that the list is being occupied and that we don't necessarily have a way to mutate it. Now, it's not necessarily a problem in Python, but in more static-oriented languages, we have to actually figure out how to compensate for this information, whether that's creating a brand new list without these red spots or manually moving each one of these spots. Well, now what if my memory didn't look that way? What if it wasn't in one specific flow? What if my memory looks something like this? Ooh, actually, I have it already drawn out. Let me see. There you go. Okay, so what if my memory looks something like this? So here we have an example of contiguous memory, where everything starts filling in from left to right. But what if my memory was something more on the dynamic side? What if I was able to create different items at separate memory spaces, but tell them how to reference to one another? Well, then I wouldn't run into the problem that we saw earlier, where if a spot is occupied, now I have to hop over to the next one or create a new link or create a new list. Now I can have items specifically know what is the next item on the list and have a dynamic spot to relate to one another. Well, that's going to be the idea of contiguous memory, which falls into our list, and dynamic memory, which falls into our linked list. All right, does anyone have any questions over this so far? All right, if no one has any questions, then let's go into actually making some code. So we just talked about occupying a memory space per each individual entry. I'm actually going to utilize a little bit of object-oriented programming to be able to create this. So the first thing I'm going to do is I'm going to create those dynamic spaces. Each one of these red squares is known as a node. So I want to create a node. And just like in regular OOP, this is going to have an init method that will hold data. And then from there, we're going to say self.data is equal to the data being passed in through the argument. And then we're going to say self.next is equal to none. So every time I create one of these nodes, it's going to be created with specific data. And this .next is going to be representing this pointer. This purple arrow is what will be dictated by this .next. Well, what does that look like? Let's go ahead and create a couple of nodes. Let's say node 1 is equal to a node that holds the number 1. Node 2 will be node it's equal to 2. And node 3 is equal to the node with the number 3. Now, each one of these independently don't know about one another, right? Right now, all I have is 3 boxes with numeric values, but they have no idea what the link is between each one. So how do I make them connect from one to the other? So just looking at this block of code here, can anybody tell me what I would change about node 1 to tell it that the next element is node 2? Go ahead, Tom.
You would change like in node 2, you would say you'd add a line underneath node 2 and you'd say node 2 dot next equals node 1. That way you're like linking the node inside as an instance attribute.
Awesome. Yeah. The only thing that I would change is that rather than noding from node 2 to node 1, I would want node 1 dot next to be equal to node 2. And same thing, node 2 dot next would be equal to node 3. Now there's going to be no other nodes, so node 3 will still be an empty list. So let's go ahead and draw this out. Let's say this is going to be N1, N2, and N3. Well, what I just made here is I told node 1 that its next element will be node 2. I told node 2 that the next element will be node 3. And I told node 3 that it has no other element to demonstrate. That's it. It's over. Goes into none. All right. Well, now let's take a look at what that looks like if I wanted to print it out. Let's say I want to print node 1 dot data. Well, node 1 dot data would give me what's that? Node 1 dot data gives me 1. Well, what if I want to see node 1 dot next? Well, when I run this, it tells me that the next one is going to be a separate node in a separate memory location. Well, now what if I want to see the data in my next node? What would that look like? How could I fix that here on line 41? I want to see the data in my next node.
Node dot two data.
Sorry, could you say that again, Athena? I think you're breaking up.
Node dot two at, wait, no, node 2 dot data.
Well, node 1 dot next, the dot next element is node 2. And if I want to see the data of node 2, I can say dot data all over again. And when I run that, it shows me that I am now looking at node 2. So I say node 1 dot next. That's accessing node 2. And when I grab dot data, what I'm actually accessing is the data attribute from node 2. All right, I can also access the dot next attribute to take a look at node 3. And I can ask it to print out the data of node 3. Now we can see the number 3 is being printed out because I iterated, started at node 1. I went into the next node, which was node 2. From that node, I went into the next one, which was node 3. And I printed out the data. Well, now let's say that we have something a little bit more complicated. Let's say we have something like node 4 is equal to node 4 and node 5 is equal to node 5. Well, rather than linking from node 3 to node 4 and then to node 5, let's say I decided that node 4 is not applicable. I don't need it. How could I link node 3 to node 5?
Node 3 dot next equals node 5.
All right, so node 3 dot next is equal to node 5. Okay, and then finally I can do node dot next dot next dot next dot data. And when I run this example, we can see that it gives me 5. So it goes from 1 to 2, from 2 to 3, from 3 to 5, and grabs the data element of the integer 5. Now, this is still just a class, right? I can give this a representation method. And if I didn't want to have to type in .data every single time, I can just return self.data. And by doing this, instead of specifying dot data, I can just take a look at the next element. Ooh, return non-string type object. Okay. See if that works better. There you go. It still gives me the number 5. Does anyone have any questions over how to connect these separate nodes? Go ahead, Eric.
So can you do a node 3 dot next dot data to get the data from node 5?
Node 3 dot next. Yes, I can. I can go into node 3 and ask it what's going to be the next value. And it will still show me the data from node 5. I can
But
go ahead, Eric.
I was just I don't know if you're about to get into it, but if you add the dot data to the end of it, would you get 5 still?
Yeah, I would still get 5. Because I'm still accessing the same instance. It's just rather than utilizing the representation method, I'm actually grabbing the data out of it.
Okay, thank you.
Of course. Will?
I know you probably will get to this, but what if one of the nodes gets deleted? So like everything else just falls off, like after that?
That's a great question. Yeah, we're going to go into that here shortly once we start going into manipulating linked list. But that is awesome. Any other questions? Okay, so now we've created this this attachment of nodes, right? And we have them all connected to one another. But now I'm actually going to create a linked list that is going to take in self. And then I'm going to tell it self.head is equal to none. And sorry, this will not take in self. There you go. So there's my linked list. Currently, my linked list doesn't know that anything exists because it doesn't have a head. A head would be where it starts. So in the example that I have up here above, where I'm connecting each individual node, how do I connect them? Where would my linked list start? What is the head of this linked list? At node 1, exactly. Not at dot data, just the actual class instance of node 1. So what I can do now is say a list of numbers, and we'll even say this is link list of numbers is equal to link list. It's going to start the instance. And then I can say list of link list of numbers dot head is equal to node 1. Nika, that's a really good observation that I see on the chat. We'll have to address that question on one-on-one. But I'm not exactly sure off the top of my head as of right now. All right. So here we've created a linked list, and we can see that the linked list has a head at node of 1. Okay, great. Well, what does that look like then now? What if I print linked list dot head? What is that going to tell me? Well, linked list dot head gives me 1. If I try to say what's the next item in the list, we can see that it gives me 2, and so on, right? If I do next again, we'll see that we get 3. And if I do next one more time, we're going to get 5, because that's our last representation. That's our last node that we've created and connected. Does anyone have any questions over this? Go ahead, Athena.
I'm just curious why it would just be, is it just because you're only accessing that whole entire instance and not the data portion? As to why it would not be .data? Could you clear that up, please?
Yeah, definitely. So the question is, why would I want .head to be equal to the entire instance of node 1 rather than just be equal to the data? Well, my linked list needs to be holding each individual one of these nodes. It needs to know about all of these nodes. But it doesn't necessarily need to know about all of its existence. It just needs to know about the very first one. So if I gave it .data here on this node, then self.head would be equal to the number 5. The number 5 does not have a .next attribute. It does not connect to the next node. The instance of node 1, which is what we assign here, has an attribute of .next that connects it to node 2. Does that answer your question, Athena? Okay, I see yes. Awesome. All right. So now I have this nodes, right? Well, let's talk about how to manipulate this linked list. What if I wanted to add something to the beginning of the linked list? What would that look like? Well, we're working in object-oriented programming, so I know that I can create an instance method where I can insert a node at the beginning. And we can say current head is equal to, and this should take in a new node. So let's say new node is equal to self.head, all right? And then from there, what I wanted to do is say self.head is equal to new node, and new node dot next is equal to current head. All right, so what exactly is going on here? Let's take a look at this code and let's break it down. And maybe I can make this a little smaller. So there's node 3 and there's node 5. Well, let's say that I want to create my first node to be node 0, right? I'm going to create a node 0 node and I want to insert it at the very beginning of my head. Well, let's create that node. We create an instance named node 0. It is an instance of node. I'm going to pass it into this variable. So now what I'm going to do, currently right now, my linked list head currently knows about node 1. But since I'm inserting at the beginning, I don't want node 1 to be my list head. I want node 0 to be my list head. I can't just reassign it, because if I just say self.head is equal to new node, then it's just going to automatically go to the new node and it's going to lose this entire connection of chain links, right? Instead, I'm going to hold on to what the current head is by placing it inside self.head. So I'm going to hold on to this variable, saying, hey, this is the current head. And once I hold on to that variable, again, linked list currently knows about that head. Well, I'm going to change the head of the linked list to the new node. once I have that, well, now I can go ahead and take a look at the current head and assign that as the .next variable of current head. And that's how we can add a new node to the very beginning. So let's take a look at that in practice. Let's say node 0 is equal to node 0. Well, now I can say linked list of numbers, insert at the beginning, node 0. So now what happens when I print linked list of numbers dot head? So I'm going to print it the head first before we insert at the beginning, and then I'm going to print the head once we've inserted at the end. So now we can see that the first one is the number 1. And when I take a look at node 0, or the next, once I add a node at the beginning, when I print head, it gives me node 0. All right. Well, what happens if I do something like dot head dot next? What do I expect this to be?
Would be node 1.
Yeah, I would expect to see node 1. All right, we see node 1 at first because that was the original head. I gave it the new head of node 0. And when I entered next, it gives me node 1. Does anyone have any questions over this so far? Okay, so far, this is what we have in my code, right? I have my linked list. Let me go ahead and make this a little bit more smaller. My current head reference. And here's where my linked list is currently starting. Okay, well, what if I wanted to add something at the very end? What would that look like then? Let's create a method for adding something at the end. So insert at end. Again, it has self, and then it has ending node. So currently right now, my linked list only knows about head, and through head, it knows about .next. So all I'm going to do is I'm going to say while self.head .next, because we know that next will eventually be equal to none. Let me write that down here. We know that it will be eventually equal to none, but as long as it has a next, then I want to reset the head of this current instance. And let me say starting let's say original head be equal to self.head. Okay. Well, now all I'm going to do is say, well, then self.head is equal to self.next. And it's going to continue doing that over and over again until finally it is equal to none. Now, once it is equal to none and self.head is none, it's going to break out of this for loop. And I'm going to say self.head dot next is equal to ending node. Then finally, I'll reset the head back to its original value. So let's break down what's going on here. All right, so I don't want to lose my head, my original head. So I'm going to assign this to a variable named original head. So I'm just going to put OH here. After that, I'm going to iterate through each individual node and check if they have a next variable. So what is the next attribute of node 0? No one knows what would be the next attribute of node 0?
Node 1.
Yeah, so node 0 would check the dot next, and it would be node 1. Node 1 would check for dot next, that would be node 2. Node 2 would then check for node 3, and node 3 would then check for node 5. Well, now when it gets to node 5 and it checks for the next variable, it's going to get none. So this is going to continuously iterate through each individual node until finally it gets to node 5. And at node 5, it's going to assign it the ending node. So I'm just going to put ending node. And instead of being attached to none, it will be attached to ending node. Then after that, we want to reset our head to go back to the original by saying self.head is equal to original head. All right, well, let's see what this looks like in action. Let's make a node 6. We've already covered this part, so I'm going to go ahead and comment it out so we don't get that anymore. Now let's say link list of numbers dot insert at end node 6. And let's just quickly make a print statement so that we can see each individual link, right? So let's say while link list of nums dot head how do I do this? Yeah, let's just say let's go the rough way first, and then we'll go into iterating through the list here shortly. So let's print the linked list of numbers dot next dot next dot next dot next dot next. All right, that's a lot of dot nexts. Linked list of numbers dot head. I apologize. Where did I mess that up?
Is it maybe self.head equals self.head.next in the while loop?
Yeah, it's right there. Thank you. Okay, so I want too many nexus. Let's go ahead and go back one here. Okay, there you go. So now we can see that it's able to go all the way through, and that very ending node is node 6. Well, now that was kind of a pain to be able to iterate through each individual next, right? To be able to grab the next attribute. So maybe we should create a method for traversing through a linked list. So let's go through that. Let's name it traversing. This is just going to take in self. We're going to say that the current head or original head is equal to self.head. And then after that, I'm just going to go ahead and say while self.head I'm going to print self.head. I'm going to also print self.head.next. And then finally, oh, excuse me, then I'll reset the head to be equal to the next one. And before my function ends, I'll reset my head back to the original head. So here it's doing the same thing. It's going to say while we still have a self.head, so while I'm not none, I'm going to go ahead and print the current head and the next head. And then I'm going to reassign the head to be my next node. So now instead of doing a print statement where I'm trying to do .next over and over again, I can say link list of numbers dot traversing. And when I run this, we can see that it prints node 0 attached to node 1 attached to node 2, 2 to 3, 3 to 5, 5 to 6, and 6 to finally none. Does anyone have any questions up to this point?
Can you just scroll back up to the traversing so I can write that down? I was almost done and you scrolled.
Oh, I apologize. Go ahead, Tyler.
I do have a question about the while loop. Isn't like every time you're using or calling that method, it's looping through the whole linked list, isn't it?
For the traversing?
Yeah. Well, I guess for both the insert and the traversing.
Yeah, if I'm inserting at the end, it's gonna iterate through the entire list until it gets to the very end. And once it gets to the very end, then it will assign that head. If it's the very beginning, you can see here how there's no while loop. And when it's traversing from left to right, kind of like a for loop does for a list.
Okay. So then it's not so like to big O for using linked lists is still going to be linear.
That's correct. Yeah, if you want to iterate through it, it would happen in linear fashion.
Gotcha.
All right. So now the next one's going to be deleting, right? Let's say I want to delete something from my linked list. What if I wanted to delete the number 2? All right, this is what I want to delete. Oh, hello. Well, now, if I just delete the number 2, then node 1 would not know about node 3, node 5, or node 6. So if I am deleting the number 2, I need to ensure that I create a new link between node 1 and node 3. All right, so how could I do that? Let's go ahead and start creating this function for deleting a specific key. Delete by value. Right, so I'm going to go ahead and pass in self. I'm going to pass in key because I expect a key to be passed in here. So again, I'm going to keep track of my original node at the same time that I keep track of my original node, which is going to be self.head, or sorry, original head. I also want to keep track of my current node, and we'll go through that here shortly. So first I'm going to say what is my next node? Okay, so now I have my original node, my next node. All right, so how do I check this? Well, the first instance that I would like to see is what if the first instance is the very first node, right? So I can say if self.head.data is equal to key, well then I will want self.head to just be equal to my next. Oh, and I apologize, that would be that next. My next node, right? So if what I'm deleting is my very first statement, then all I'm going to tell my list to do is to make the original head, or to make my head this node, node 1. And that's it. After that, I can just return because there's nothing else that I wanted to do. Okay, so that takes care of it's my very first node. So now let's move through the rest. Well, what if it's not my very first node? Well, the next thing that I want to check is if it's my next node. If next node dot data is equal to key, then all I want to do is I want to say self dot head is equal to, or sorry, self dot head dot next is equal to my next nodes dot next. So now if I were to look at this example where we're saying that we're deleting node 2, if let's say this was the trigger, right? I go through and I'm checking node 1. Well, node 1, which is my head, the key is not equal to 2. So this if statement doesn't get triggered. So then I check my next node. My next node is node 2. If my next node dot data is equal to the key, which would be the number 2, so this is true, then I'm going to say, well, then node 1's next value will be node 2's next value. So I would be creating this bridge instead of going from node 1 to node 2. I'm telling it to go from node 1 to node 3. And if I was deleting something at the very end, which would be node 5, well, it would do the same thing. It would check node 3 to node 5. It would see that node 5 is the key. So then it would create the link to none. And then finally, I would just say, oh, self.head is equal to next node. And then self.head is equal to original head and they would return. Same thing here, self.head is equal to original head. And then return. So that would iterate through all of the nodes, check the next value. Actually, that would only do one of them. I need to put this all inside of a while loop, I believe. So while self dot head next. Then that would happen. Okay, let's see this in action just to make sure I didn't mess it all up. So I'm going to do linked list dot delete by value. And I'm going to delete the value 2. And then after that, I'm just going to run my traversing function one more time. Okay, so we see the traversing function happen from 0 to 6. It looks like I'm stuck in an infinite loop, and that's because I never moved my self.head to the next one. Which I guess I could just call this next node. Okay, so we see that first value here being printed out on the terminal, going from 0 to 1, 1 to 2, 2 to 3, 3 to 5, 5 to 6, and then finally 6 to none, which is what we expected. On the next time I traverse, we see 0 to 1, and rather than seeing 1 to 2, we see 1 to 3. Right? We deleted that value, or we deleted this bridge that we originally had between node 1 and node 2, and switched it to go from node 1 to node 3, node 3 to node 5, node 5 to node 6, and then from node 6 to none. And that is how you delete by value from a linked list. All right, does anyone have any questions regarding deleting a value? And I see a couple of questions here on the Slack channel. Let me go ahead and read through them. So you're just returning nothing? Yes, I am returning nothing because I'm trying to kill the function. That's all it is. It's not supposed to return anything. It's just the behavior has been met. So I trigger a return statement to kill my function. The next one is, how is it traversing through the nodes without a for loop? It's not traversing through the nodes because of a for loop. It's traversing with a while loop. So it's checking if there is going to be a next value. So as long as .next is not none, it's going to continue running this logic until it does find none. Oh, that was before we had a while loop. Okay, no problem at all. All right, and then I see the other question by Edge here. Is that supposed to be a self.head.head or a self.head.next? Thank you, Edge, for catching my syntax error. I appreciate it. Okay, does anyone have any questions regarding how to manipulate a linked list? Go ahead, Tyler.
So obviously, like, we manually set the initial nodes, right? So like for node 1 and node 2, we manually set like the next node for those. But obviously, the way you would really construct a linked list is just with that. Would you construct it with the linked list class? Would you just run insert at end? Like how would you instantiate without manually doing it new instances of nodes? I guess is what I'm getting at.
Yeah, definitely.
Or maybe we're gonna get into that. So
yeah, no problem at all. And actually, that's not part of our node, so I definitely should. So let's say we have a node class, we have a linked list class that we completely built out. It has all of our methods, but currently that's all we have. We don't have such thing as node 1, node 2, or node 3, right? Well, let's say that we want to create a couple of nodes. So let's say that we want to create a list of nodes from nodes 1 through 6, right? Let's say how could I do this? I have the method in my linked list for inserting at the beginning or inserting at the end. Right? So right now I have my head. Let's say I want to insert at the end, original head. Ooh, so this might cause a problem because if I check .next for none, it's going to say, hey, I don't have this. Interesting. So I may have to change a little bit of my logic here. Let's see, well, self.head. I think this should still work correctly. Let me go ahead and bring those statements back real quick just to make sure that they all work. If I remove that insert at the end, .next. Okay, where's that happening? That's happening in line 61. While self.head. Okay, so I can say if not self.head. So if self.head does not exist, nope, we don't want that either. So original head is equal to self.head, while self.head. Okay, we want that. Yeah, so if not self.head, then I want self.head to be equal to the ending node. All right, so if my list was empty and I was to add one, I would want it to be equal to the ending node and then immediately return. And then while self.head, so while self.head exists, I can still do .next. Okay, so that seemed to have fixed that. Let me go ahead and check here what would happen if I comment all of this good stuff out now. Okay, so currently let's look at linked list traversing. Just real quick so we can see that there's nothing in there. All right, so if I iterate through that and I try to print, it's going to tell me that there's nothing in there. I can try to traverse, there's going to be nothing in there. Well, now if I want to do something like this, so for, let's say something like for, I'm actually not going to save this. I'm just doing a linked expression. Let's do for number in range. I don't know, let's go for 10. And let's do from 1 through 10, right? So let's say for linked list dot insert at end. And I want to add a node of num for num in range 11. All right, so this is going to create a node for each individual number and insert it at the end. Well, now let's see if this works. Okay, so now we can see that we have a linked list where 1 is attached to 2, 2 is attached to 3, 3 is attached to 4, 4 to 5, and so on, all the way down into our last node where 10 is attached to none. Does that answer your question there, Tyler?
Yes, it does. Thank you.
Of course, no problem. That was a good question. Thank you, because I totally missed that if statement at the beginning. It's kind of like handwriting the append function, right? Any other questions regarding linked list? All right. If there are no questions, I'm going to go ahead and open up the floor for Adam. Adam, I know you're present. Is there anything that you would like to add to linked list?
No, this is awesome. Just welcome to the world of linked lists. And kind of part of the value of practicing this stuff is even if we're not directly implementing linked lists ourselves, you'll see similar patterns pop up as we start to work with like more and more complex data structures. And also I think just this flexes skills that then help us in other domains as we continue to write code and design programs.
All right, awesome. Edge, I see you have a question.
I guess I'm sort of just confused. Doing the list comprehension there on line 100, does that not create a list? Like, aren't you're creating a linked list, but also just a regular list in memory? Or am I missing something here?
Yeah, this is not actually getting stored in memory. This is just conducting a function. The only thing that's
Oh, just because we haven't assigned it to a variable, or why is that not actually saving anything?
Yeah, it's because I haven't assigned it to a variable. So if I
Okay.
had it assigned it to a variable, then it would just be multiple linked list. I guess it would be a list of linked list. Whereas this one would just, I'm not assigning it to anything. It's just conducting the behavior within the list comprehension. Is
Okay.
that a question, Edge?
Yep. Thank you.
Of course. See a question from Tyler.
Sorry, would you be able to just really quick go back through the logic of the delete value?
Yeah, of course. Let's go ahead and go through the delete value real quick. So the delete value is going to take a look at the original head. So it's going to grab head. It's going to ask while the head has a next variable. So if our head actually has a next variable, then I'm going to go into this while loop and execute this information. So this while loop is going to say, all right, well, the next node is self.head.next. All right, so now I'm telling it, this is currently my next node. So node 1 currently knows about node 2. I'm currently on node 1. My next node is node 2. And it's going to check, hey, is my self.head, so it's currently the value that I'm trying to delete, number 1? It isn't. So it's not going to go into this if statement. So the next thing I'm going to check is my next node, node number 2. It's going to say, hey, is next node, the key, what I'm trying to delete equal to the data. So if I was trying to delete the number 2, which is what I have here on this example, what I'm going to do is I'm going to tell my current head, which is node 1, that its next node is going to be number 2's next node. So it's going to take a look at number 2, see that node 2 has a link to node 3, and it's going to create a new bridge where node 2 and node 1 are no longer connected. So now when I go through my linked list, node 1 is connected to node 3, and node 2 is now separated from the chain links. And then after that, I just say my self.head is equal to my original head. So I'm resetting my head from going to node 1 back to node 0, and then I'm returning my function. Does that answer your question, Tyler?
So what if the current head data value is the key and that's what you're trying to delete? I guess I was confused on that, like the self dot head equals next node and then self dot head equals original head, because original head is set to self dot head. Like it just seems like I don't it how does that delete it if it's reassigning self dot head to the original head, which was the original self dot head?
Got it. So let me go ahead and go through that, right? So here's our original head, and then I'm just going to utilize purple to mark what the current head is, right? So we mark our original head. Oh, let's make that blue. Our original head is marked. So the first thing that I evaluate is, does my original head, which is number O, right? Does this head have a next value? My next value is node 1. So it does. Okay. So now that it checks that my node value is next 1, it goes into line 77. So now I'm saying my next node is node 1. So there's my next node. And then I ask it, is this current head equal to the key? It's not. Is my next data, my next node's data equal to the key? Okay, it also isn't. So now I'm going to say, well, now my head is going to be equal to my next node. So now my head is equal to my next node. And it goes through my while loop again. It says, all right, well, does this new head, which is node 1, have a dot next? It does. It is node 2. So there's my next node is self.head.next, right? Because now the head is node 1. And now I'm going to say, hey, is this current head equal to the key? Well, it isn't. So it goes into the next head or the next node. And next node, it's going to ask, is node 2 equal to the key? And in this case, it is. So now I'm going to tell the current head that I'm on, which is node 1, to go from node 1, look at node 2, take a look at what its next value is, which is node 3, and create a bridge connecting node 1 to node 3. Since that is triggered, and I know I'm about to kill my function, I can't just return it and let it end, because in my linked list, the head would be left over at node 1. And I don't want that. I want it to go back to node 0. So right before I kill my function with a return statement, I tell it self.head is equal to the original head. So it comes back up to original head so that it can reset and restart anytime I go through my linked list. Did that answer your question, Tyler?
It did. Yeah. Thank you very much.
Of course. I see Yams asking a question regarding line 80. Let me take a look here. Self.head equals original head. Yes, we do. Did the example that I just went over and address that question right there, Yams?
It's just, it looks like 78 was protecting if the first node was the one that we wanted to delete, and we don't want to keep that, right? Is that
line 78?
Yeah, is that what that was? Is if the first node was the one that we wanted to delete, then we don't want to keep it at line 80, I think.
Oh, I see what you're saying. So what if the original head, if that was the very first node? Interesting.
Yeah, that may be an edge case. That's definitely an edge case. That's a good edge case.
Yeah. I guess we could definitely put an if statement here saying if self.head is equal to original.
It looks like if we delete line 80, I think that should be it.
Well, that would
Well,
fix
we
it
would,
for that problem, but it wouldn't fix it for the later on problems.
yeah. I think I agree with you, Francisco. I think we need to throw in like a conditional saying if the thing we want to delete is the first thing, we need to update original head to point to the next thing.
E does not equal to original head dot data. There you go. And that should do it. So let me see. If I traverse through it right now, we can see that I have 1 through 10. So let's say that I wanted to remove 10. So, I mean, is 1. Linked list of nums traversing. There you go. So now we see that it's the first one. That goes to the first traversing. After that, I remove the value of 1, which is my very first node. And now we can see that it was reset correctly. And let me just do a sanity check here by checking what happens if I delete node 3 instead. 1, 2, 2, 4. Yep. Okay. That did the trick. Just needed
Oh,
to a special edit case.
actually, could you explain how that works again, Francisco? I might have made a bad assumption that we would have to like reset the original head, but it looks like we don't have to when we want to delete the first thing.
Yeah. Of course. So what this is doing is it's still following the same logic, but just like Yams mentioned, what if the one that I wanted to delete was the very first index, right? Well, if it was the very first index, I wouldn't want it to get reset to the original head, because if I reset it to the original head, I would essentially always keep the very first index. So what I'm asking here is if the key is not
Oh,
head, then I could reset it to the original head.
got it. That's simpler. That makes sense. Thank you. We just don't have to think about the original head. And then at the end of the while loop, we set head to the next node and we're good to go.
Right.
Thank you.
Current node and current node dot data not equals key. Yes, I know the lesson has a bit of a different code than what I do. I try to make my code a little bit more readable by naming it current head or original head, next node, and all that stuff. Hopefully that did the trick. Otherwise, if you look at our nodes, everything is just named a node, and it could get a little confusing if I just use the same variable. Yeah, of course, no problem, Nika. Okay, if there are no other questions, this is going to conclude our lecture. Today we covered, oh, that's not what I meant to do. Today we covered computer memory, what is important about computer memory, why should I know computer memory, what happens when I create a list. We utilize the ID and hex functions to actually get that memory address. We went over constructive and destructive methods of manipulating lists. We also looked at the amount of size that is being occupied by different data structures, utilizing the system get size of, and we utilized list and tuples to compare one another and get the differences in their size in memory space. Then we talked about an efficient code example, such as list comprehension versus stretching out a list through appending. Then during the part 2 of our lecture, we covered linked list, what's wrong with list alone, falling within our actual Python programming, and how to utilize linked lists to mitigate this problem. At this point, does anyone have any questions regarding any topic that was covered today? All right, it doesn't look like there are any questions. I'm going to go ahead and stop the recording.